Here's something wild. You've probably lit hundreds of fires in your life. Birthday candles, barbecues, maybe a fireplace. You know exactly what to expect. Flame appears, heat radiates, things burn, routine stuff. But have you ever stopped to wonder why any of that happens? Most of us don't. Fire is just fire. It's been around forever. We use it, we control it, we move on. But when you actually stop and ask what's really going on when something burns, you stumble onto one of the most elegant secrets in nature. A secret that connects dying stars, ancient forests, and the air you're breathing right now. Fire isn't just some random phenomenon. It's a doorway into understanding how matter behaves, how energy transforms, and why life itself is possible. Let me walk you through it. The waiting game picture: a piece of firewood, dead tree, bone dry, sitting on your back porch, and all around it, oxygen molecules drifting through the air, both just existing, both completely stable. Here's what's strange. The wood has been there for months. The oxygen has been swirling around it the entire time. They're in constant contact, and yet nothing. No reaction, no fire, just wood and air coexisting peacefully. But here's what you don't see. At the atomic level, there's this incredible tension. The carbon atoms locked inside that wood and the oxygen floating in the air, they're actually attracted to each other strongly. If they could combine, they'd release massive amounts of energy and settle into a much more stable configuration. So why don't they? Think of it like this. Imagine two magnets that desperately want to snap together, but there's a wall between them. They're attracted, but they can't reach each other. They need something to knock down that wall first. In chemistry, we call that wall the activation energy barrier. The carbon and oxygen atoms are constantly colliding, millions upon millions of times every second, but they're not hitting hard enough. They bounce off each other and drift apart. Again and again, year after year, that piece of wood could sit there for a century, surrounded by oxygen, and absolutely nothing would happen. The atoms want to react, but they're trapped on the wrong side of the barrier. The spark that changes everything. Now, what happens when you introduce heat? A match flame, a lighter, even focused sunlight through a magnifying glass? You're doing something crucial. You're giving those atoms extra energy. You're making them move faster, jiggle harder, collide with more force, and suddenly a few of them hit hard enough to get over that barrier. They get close enough that the attraction takes over, and snap, carbon and oxygen lock together. And here's where it gets beautiful. When those atoms combine, they don't just sit there quietly. They release energy, lots of it. That energy makes the surrounding atoms move even faster. Those atoms hit harder, get over the barrier themselves, and snap together too. And they release even more energy. One reaction triggers another, then two more, then four, then eight. It's exponential. Within fractions of a second, you go from a handful of reacting atoms to billions of them, all combining simultaneously in a cascading chain reaction. That's fire. That's the moment of ignition you see. It's not gradual because it's a feedback loop spiraling out of control. The heat from the first reactions provides the energy for more reactions, which create more heat, which triggers even more reactions. It feeds on itself. This is why fire seems almost alive, why it spreads and grows. It's a self-sustaining process. Every reaction makes the next one easier. The system bootstraps itself into this wild, energetic state. What heat really is. So what exactly is happening when you feel the warmth of a fire? Heat isn't a substance that flows like water. It's not some invisible fluid pouring out of the flames. Heat is motion, atomic motion. When we say something is hot, we mean its atoms are vibrating intensely, bouncing around at high speeds. When fire releases energy, that energy transfers into kinetic energy. Atoms start moving faster. They collide with neighboring atoms, making those move faster too. The jiggling spreads outward. Hold your hand near a flame, and you're feeling atoms in the air being knocked around so violently that they start knocking around the atoms in your skin. That sensation, that warmth, is just high-speed atomic collisions. And fire itself, what is it really? It's not a thing you can hold or bottle. Fire is a process, an ongoing event. It's this runaway cascade where atoms are frantically snapping together, releasing energy that makes other atoms snap together even faster. It's a wave of chemical transformation sweeping through matter. That's why fire spreads. That's why it's so hard to extinguish. The heat sustains the conditions needed for more reactions. Break that cycle by removing fuel, cutting off oxygen, or cooling it below the threshold, and the whole thing collapses instantly. Sunlight in reverse. Now, here's where this story takes a turn that should absolutely blow your mind. Where did that wood come from? A tree, obviously. And what is wood made of? Mostly carbon. Okay, so where did the tree get all that carbon? If you're like most people, you'd say the ground. Trees grow from soil, right? Plant a seed, water it, and the tree pulls nutrients from the earth. Wrong, almost completely wrong. The carbon in a tree, the very substance that makes up the bulk of its mass, comes from the air, from carbon dioxide gas floating invisibly all around us. I know that sounds absurd, but here's proof. Take a pot of soil, weigh it carefully, plant a seed, water it for 10 years. Let the tree grow massive and heavy. Now dig it up and weigh the soil again. The soil weighs almost exactly the same as it did before. Maybe a few ounces lighter from some minerals the tree absorbed, but the tree now weighs hundreds of pounds more than it did as a tiny seed. That mass didn't come from the soil. The soil didn't lose hundreds of pounds. The tree pulled it from the atmosphere. A Dutch scientist named Jan Baptist van Helmont actually did this experiment in the 1600s. He was shocked by the results. The soil barely changed weight. He concluded correctly that trees don't grow from the ground. He thought they grew from water, which is partially true, but he missed the main ingredient, carbon dioxide from the air. The sun's secret job. But wait, there's a problem here. Earlier I told you that carbon and oxygen are incredibly attracted to each other. They snap together and release tons of energy. That's what fire is. So how is it that trees can rip carbon dioxide apart? How do they separate carbon from oxygen when those atoms are so tightly bound together? The answer is astonishing. The sun does it. Sunlight streams down, hits the leaves of a tree, and provides the energy needed to tear carbon dioxide molecules apart. The tree captures that light energy and uses it to break bonds that normally wouldn't break. It keeps the carbon to build itself and throws away the oxygen as waste, releasing it back into the atmosphere. This is photosynthesis, and it's the opposite of fire. Fire takes separated carbon and oxygen and slams them together, releasing energy. Trees take bonded carbon dioxide and rip it apart, storing energy in the process. Think of it like lifting a boulder up a hill. It takes work, requires energy input, but once the boulder is at the top, it has potential energy. It wants to roll back down. The tree uses sunlight to do that work, to push the system away from equilibrium, to separate atoms that want to be together. And that separation, that's where the energy gets stored. In the structure of the wood itself, the carbon and oxygen are held apart, waiting. Fire is stored sunlight. Now imagine you cut down that tree, let the wood dry, and toss a log into your fireplace. You strike a match, the fire starts, and suddenly your room fills with warmth and flickering light. What's really happening? All that carbon the tree spent years pulling from the air, all those chemical bonds it built using captured sunlight, they're collapsing back together. The carbon is reuniting with oxygen from the atmosphere. The potential energy stored in the wood structure is being released. The light dancing in those flames, that's sunlight. The same sunlight that fell on those leaves 5 years ago, 10 years ago, maybe 50 years ago. It got trapped in chemical bonds stored in the wood, and now it's pouring back out all at once. A burning log is the sun shining again. Every photon flickering from the fire, every bit of warmth you feel, it's recycled solar energy. The sun powered the tree's growth. The tree stored that power, and fire releases it back into the world. That's what fire is. It's not destruction. It's transformation. It's stored sunlight, escaping. The question that haunts you. But this should make you wonder, if carbon and oxygen are so desperate to be together, if combining releases all this energy, why doesn't wood just spontaneously burst into flames? Why does it need a match? Remember that barrier I mentioned, the activation energy. At room temperature, atoms aren't moving fast enough to get over it. They're bumping into each other constantly, but not reacting. The wood and oxygen exist in what we call a metastable state. They're technically stable, but only because they're stuck. Think of a boulder perched at the top of a hill. It wants to roll down. That's the lower energy state, but it's sitting in a shallow depression. It's stable there unless something disturbs it. Give it a small push, and it crashes down, releasing energy as it goes. That's what a match does. It provides the initial push. It heats a tiny region of the wood, making those atoms move faster, helping them over the barrier. Once a few reactions start, they generate enough heat to trigger more reactions. The fire bootstraps itself and spreads. This is why the universe doesn't just explode. It's full of metastable systems, pockets of stored energy waiting for a trigger, wood and oxygen, gasoline and air. Even the food in your stomach and the oxygen in your blood, they're all waiting. And when they get the right trigger, they release their energy and transform. The oxygen paradox. Here's something that should completely reshape how you see the world. The oxygen in the air, the stuff that makes fire possible. Where did it come from? From trees, from plants, from billions of years of photosynthesis. Plants rip apart carbon dioxide, keep the carbon for themselves, and dump the oxygen as waste. They don't want it. It's garbage to them. Every breath you take is filled with plant waste. Early Earth had almost no free oxygen in the atmosphere. It was mostly carbon dioxide, nitrogen, and water vapor. Then photosynthetic organisms evolved. Cyanobacteria, ancient algae. They started pumping oxygen into the atmosphere as a byproduct of their metabolism. For many early life forms, oxygen was poison, toxic. The Great Oxygenation Event, as it's called, was one of the first major extinction events in Earth's history. Oxygen killed off countless organisms, but some life adapted. Some organisms evolved to use that oxygen, to burn fuel with it, to extract energy from it. And those organisms, our ancient ancestors, thrived. The circle closes. So here's the full cycle, the grand pattern that connects everything. The sun shines. Plants capture that light and use it to break apart carbon dioxide. They build their bodies from carbon and release oxygen as waste. Animals eat those plants, or eat other animals that ate plants. And then we burn that carbon-based fuel by combining it with oxygen, releasing the stored energy. That burning happens in your cells right now. It's called cellular respiration. It's the exact same process as fire, just slower and far more controlled. You're taking sugar molecules, combining them with oxygen, and releasing energy to power your body. The carbon dioxide you exhale is the same carbon dioxide the plants absorbed. The cycle repeats endlessly. Carbon circulates, oxygen circulates. Energy flows from the sun through life and back out again. Fire is just that cycle made visible. When you burn wood, you're doing what your cells do when they metabolize glucose. Same chemistry. Carbon plus oxygen yields carbon dioxide and energy. The only difference is speed and control. Your cells do it gradually, carefully, capturing the energy in useful molecules. Fire does it explosively, releasing everything as heat and light. But fundamentally, chemically, it's identical. You are, in a very literal sense, a controlled fire. The mechanics of flame. Let me get even more specific about what you're seeing when you watch a fire. The heat you feel, that's kinetic energy. Atoms vibrating, molecules spinning, electrons jumping to higher energy levels because energy was released when bonds formed. The light you see, that's electrons getting excited, literally jumping to higher orbits around their nuclei, and then falling back down. When they fall, they emit photons. That's the glow. Different elements emit different wavelengths, different colors. Sodium glows yellow, copper burns green, strontium flashes red. That's the entire principle behind fireworks. Different chemicals produce different colored flames because they have different electron structures. The smoke rising from a fire, those are tiny particles of carbon and other materials that didn't fully combust, floating upward because they're hot and less dense than the surrounding air. The ash left behind, that's the minerals, the trace elements the tree absorbed from the soil, the bits that didn't come from the air. Everything else, all the carbon, hydrogen, and oxygen, has turned into gas. Carbon dioxide and water vapor, invisible, drifting away. The mass didn't vanish. It transformed and dispersed. One last question. So now you understand fire. It's a chain reaction. It's stored solar energy being released. It's atoms colliding and bonding and releasing energy that makes more atoms collide and bond. But this should leave you with one final question, the question that opens up an even bigger mystery. How is the sun itself so hot? What makes it jiggle so violently that it can power all of this? trees and fire and life and everything. That's a different story entirely, a story about gravity and fusion and the birth of elements in stellar cores. But I have to stop somewhere. I'll leave you with that to wonder about. For now, next time you light a candle or sit by a campfire, remember, you're watching sunlight escape. You're seeing stored time being released. You're witnessing the universe playing out its most fundamental pattern, the endless transformation of energy and matter, the dance of atoms that makes everything possible. Fire isn't just fire. It's a window into how everything works.